dark matter paradigm. Please go.
No, thank you very much for the invitation. For me, it's very nice to be here at the Instituto de Astronomía. I like to be here. And I will try to explain several things. First one is which is the standard model of cosmology, or what we call the standard model of cosmology. This is very simple, and why we think or we thought that this model was the candidate to be the solution and the explanation of the dark matter and the dark energy. That means it's the accelerated expansion of the universe together with the dark matter. This anomaly that we see in galaxies, clustering of galaxies. And after that, I will remind you some of the problems, some of the open questions about these models. And after that, I will explain some of the alternatives of this we have. And I will focus only on the most interesting, or at least the most known of them, of these alternatives, because there are so many alternatives. Almost each physicist in the world, each astronomer in the world have an alternative for dark matter, another for dark energy. And if you walk at the street and ask the people that know a little about the cosmology, they will say, yeah, the dark matter is something and so like that and that and that, and another universe and something like that. Everybody has an alternative. Okay, but I will explain some of the most interesting ones. Well, the standard model, and this is a very, very interesting and very, very nice model. The standard model of cosmology is such that we have a cosmological constant proposed by Einstein in the 20th, in the last century, and the dark matter is something called dark matter, called dark matter, and this is a dust. This is a perfect fluid with a zero pressure, pressure less. Well, that means you have the Friedman-Robson-Walker metric. That means the universe is homogeneous and isotropic. Matter is pressureless like the dark matter. That is the hypothesis. The dark energy is the cosmological constant that the pressure is equal to minus the density. And then what we know is that radiation, neutrinos have this state equation. And that's all. And you can add any things that you want. But the most important things, or the most important stuff of the universe is given here. Of course, it is not enough. Because if we want to explain everything, if we want to explain the universe, we have to add, for example, the information inflation. This is another theory. And we have to add, for example, here something like a scalar field or something related with scalar fields that plays the role of an inflaton. Then we have to take into account the standard model of particles in order to explain the Big Bang nucleosynthesis, and of course the cosmic microwave background. And then we can, with this theory, we can explain the structure formation of the universe and everything else. Well, then this is not so simple, but as you see, this is the most simple model we can imagine. Well, then the history is very simple. Then you have the Big Bang. What is that? We don't know. All what we know is that in this region, the universe is very, very dense, very, very hot. And then after that, there is a period of inflation. That means a very small, short time, 10 to the minus 10, 32 seconds, and the universe expands from 10 to the 100 times. And after that, the 318,000 years later, we have the transition where the universe, the photons and the rest of the matter is not more interacting, and then we can see all of this structure, and this is what we call the CMB, the cosmic microwave background. And then we have the dark age and the formation of structure. That means stars, clusters of galaxies, etc. Well, that is the idea. And the paradigm of the lambda cold dark matter is constructed in the following way. The dark matter fluctuations spectrum at recombination is determined by a small number of physical parameters. And after recombination, the amplitude of the baryons fluctuations rapidly grows to match that of the dark matter fluctuations. Then small mass fluctuations drop to non-linearity and be realized, and then hierarchically clustering or cluster within successfully large bond systems. That means the small structures will collide with other structures, small structures, forming bigger and bigger structures, and so it's hierarchically bound. And this is the galaxies come from the small halos come together, and then bigger halos come together, and so on, and then form these halos that we know today. Well, this is very important because it can be a problem. And ordinary matter systems with 10 to the 8 to 10 to the 12 solar masses cools rapidly enough within the dark matter halos to form galaxies, while larger masses fluctuations form clusters. This is the idea, and of course there are a lot of work done in this direction. You see here, this is a numerical simulation using I think 14,000 computers here. This is to redshift 18.3. Later in redshift 5.7, you see the structure formation. And in redshift 1.4, you see the structure formation. And today we see a very big structure formation. And that is what we can compare with observations. For example, today we have the DESI observations and Beria Rubin observations in the future. And in the past we have the Bose observation and so on. Well, and the good news is that the theory here is in the red line here is the cold dark matter line, and here is this green line. Yes, and the stars here and the points are the observations, and this is the cosmic microwave background. You see, they are very well fitting with the theory, with the model in both cases. And therefore, we thought that the lambda cold dark matter was the best answer because it's very simple and has fits very well the observations at big scales. Okay, and of course we have to have a candidate. This is what I said. This is a dust. This is a perfect fluid with pressureless, and this is a dust. But which candidate? Well, any candidate which we can take is enough if we have enough amount of this stuff of this candidate in the universe. And this is the formula you have to follow in order to have the candidates. There are many of them, many. For example, axions, sterile neutrinos, you see particles, primordial black holes, and so on. All of them can fit all of this structure. And of course, we have to look for them. And if we have observations, and there are two ways to observe them. This is detection or production of from annihilation or decay of these particles, or interaction with nuclei in underground detectors. This is the two ways we are trying to detect all of these candidates. For some years, I think this group of astronomers, they claim to detect the dark matter, and this is all. This is the Dama Libra observation. The sun is here. The Earth is going around the sun, and in this direction you will have an amount of dark matter, and the other direction we have another amount because you are going in the contrary direction. And they claim that they are detecting the dark matter because they observe these points here all the time. And this was a very interesting observation, and this one in 2010. And they were claiming that they observed for the first time the dark matter, winds in the dark matter. Well, other detector is the ice cube. This is a tubes in the south continent here in the ice, and the neutrinos and the dark matter must contact these tubes, and we have to detect here the dark matter. Of course, they are detecting neutrinos all the time, but so far they don't have detected the neutrinos, the dark matter.
Dama libra or not astronomy.
No?
No.
Particle physicists.
Yes.
Yeah. Okay, particle physicists. This detector is also for particle physicists. Is 2,400 meters inside of the Mediterranean Ocean, and they wanted to detect again the neutrinos, of course, and dark matter. The problem is that inside of this part of the sea, they found a lot of animals, and all of them have electrical charge and a magnetical charge, and they were mixing with the detections of the rest of the. But they solved the problem, and they have so far they don't have detected any candidate for dark matter. Other detectors are, for example, the GLASS, the MAGIC, and the HESS telescopes, trying to detect gamma rays or something that can say us that the dark matter is there. For example, if the cold dark matter or the dark matter is axions or something that decays in photons, you can detect these photons with these detectors, but so far all of the detections were related with other phenomena, but not with dark matter. Of course, the LHC, in 2009, they discovered that the supersymmetry is not in this energy, but this is not meaning, it doesn't mean, means that the dark matter doesn't exist. That means that the minimal supersymmetric model, this is most simple model of supersymmetry, is ruled out, but not the other one, because there are a lot of candidates to be the dark matter in these supersymmetric theories or in these supersymmetric models. Well, they are looking for new detections, but so far they don't have any. Well, the most believed candidates are the WIMPs, weak interacting massive particles, and there are a lot of them. Axions are in many range of masses. This is the mass of the particles. Then the WIMPs themselves, supersymmetric particles, are here. Then qubits here, WIMPsillas that come of supersymmetry are here, primordial black holes, and so on. You see, and here, 10 to the minus 21, there are another candidate as the two ultralight candidates of dark matter. And that means the candidates amount. This is a lot of candidates. And the detection is here. This is 2019. But I saw a paper with a little with more observation of that here, with an update of these graphs, and the result is the same. Therefore, I left this picture here. You see, Shannon 1 ton and Shannon 100 were the most interesting observators. This is using in underground detectors, and they don't see anything so far to here. And here's Dama, that what I saw. That is Dama is in contradiction, is in tension with the observation of the rest of the observers. And this is, therefore, this is. And this is the last one. This is the last one, but this is equivalent to the last I showed in the last class. Well, okay. Then, which are the problems of the standard model, the lambda cold dark matter model? Well, it has a lot of problems, but I will focus only on the most interesting one and maybe the most that we have to solve. The first one in these three first problems are for that energy. The first one is extreme fine tuning. That means the cosmological constant is in tension with all the modern models of particle physics, supersymmetry, standard model. So they cannot find any form to explain the value of the cosmological constant. And therefore, this conducts to this coincidence problem. That means the cosmological constant has exactly the value that we can see them, you can see it today and not before. And this is something very strange. And of course, it's in contradiction with the DESI observations, because in the last time, DESI had observed that the cosmological constant of this energy, that energy must vary. That must depend on time, and it cannot be a constant. And then these three problems, then they have another one. This is, if you measure one of the most important constants, is the value of the Hubble constant today, and you measure that with very long observations, for example, CMB, and compare that with the close by observations, for example, the BAIO or cosmic sensors and so on, then the value is completely different. And this is what we call the H0 tension. And all of them is because the dark energy maybe is not the lambda, the cosmological constant. And it is now in really very hard tension. That's all of these four observations are all from the that energy. And then for the small scales, for big scales, the lambda color matter is really very, very nice, fits very, very well with observations. But when you go to the small scales, when you go to, for example, with galaxies or small galaxies or some far galaxies, the problems begin. For example, in the center of the galaxies, you see that the theory, that in this case, the lambda color matter says that you have a Cosby central density profile, and when you look to the, for example, to small galaxies, far galaxies, or LSB galaxies, they don't have this feature. Then other problem is the lambda color matter predicts a lot of satellites around big galaxies, and we don't see that. The voids in the theory are with a lot of galaxies, and we see that they are almost void, and no detection of dark matter theory. Let me explain first the H0 tension. Here is you see in here is all of them. I cannot see that. But this is the CMB observations, and here the rest is the other one. And you see the error bars are small enough to say they are in intention. You see when you measure this H0 constant with very far away observations, you have a value. When you observe that with other value, with other observations, for example, here are the BAO and the cosmic sensors and other one, and the supernovae, all of them have another value. And this is of course a very interesting thing. And you see here the evolution. This is a evolution of the H0 value obtained by observations. You see there are big error bars so far. This is not so very well resolved. But in any case, you see for big redshifts, you have a value, and for small redshifts, you have another value. And therefore, you see the variation of the cosmological constant could be the solution of this problem. Well, now I will speak very few about these two problems here. And of course, the lambda color matter model solves most of these problems somehow. And I will say how, okay? They are problems, but you can also claim that you have another physics or another way to go around this problem, okay? And I will explain that. Okay, the problem of the Cosby central density profile is because if you go to the observer density, you have the density in the center of the galaxy goes like 1 over x to the alpha, but the observer one is alpha between 0 and 1. And for lambda color matter, for the cosmology, for the standard model, the value is exactly 1, but we don't see that. Well, this is one very old observation of many galaxies, and you see this point. And here again, this is the observed is here. This is the line is for the core observations, and the other one is for the lambda polar matter. Here is lambda polar matter in Navarro frame white profile here, and you see there is a problem, and everything goes here, and lambda polar matter is this brown line, and you see there is a difference between them. And in the last time, these astronomers have found that the galaxies here around, they have all of them the alpha very small, close to 0, and Navarro frame white is alpha equal to 1, and therefore this is a discrepancy. And furthermore, he found that the product between the density, the central density of the galaxies times the size of the core is almost a constant in all galaxies he measured. And this is very difficult to be explained by the lambda polar matter. Nevertheless, they claim that there exists another physics. This is also true. For example, here uses a numerical simulation of the formation of a galaxy, and the galaxy is forming, but you have to take into account, for example, the explosions of the supernovae, and you have to take into account the movements around the center, but they are not circular, but they are other kind of movements, and so on. And if you take into account all of these facts, you will find that the density profile fits very well with the observations. Here is the fit. This is a Nature in 2010. This is the fit, and the line is the fit with using all of these physics, and the points are the observed one. And you see, there fits very well. Nevertheless, this formation of so many galaxies, supernovae in the center of the galaxy will provoke a lot of metallicity, the formation of metals. And this could be a problem, but they can solve this problem using another physics, and at the end of the day, the problem of the central density profile could be solved using this extra physics. And here is another small problem. The mass of the halo is given here. The predicted masses in comparison of the mass of the stars is given here, is by this line here. But the observed ones are here. Of course, you can again climb to another physics, and somehow you can solve this problem using extra physics. And then in the last time, with other extra physics, we can solve this problem. The lambda polar matter can solve this problem. The next problem is the amount of satellites around big galaxies. The lambda polar matter predicts, here is this ground line here, this line here, is the number of satellites they are predicting, yes? And this is the amount of galaxies they are observing, yes? And they claim, okay, these halos exist in the universe, but we cannot see them because they are too small to collect stars, and therefore we cannot see them. Okay, of course, we can see them, for example, using microlensing or other methods, but so far we don't see them. But in any case, they can exist, they could be there, but you see, this is what we see in measure in real. This is Milky Way, and this is Andromeda, and this is what we measure. The red line is what we can obtain using numerical simulations, and this gray line is exactly the number of halos they predict. But they claim all of these halos, they are able to collect stars, and therefore we cannot see them. Okay, this is a solution, and it is possible that this is solved. But in the last time, in 2016, the Spitzer telescope had observed in the center of the galaxy. The problem of the center of the galaxy is that the center of the galaxy has a lot of dust, and dust is not transparent to the lines of the photons in what we observe. Then we have to see that in red color. or in infrared color. And this satellite can see that in infrared colors. And what he observed is that in the center of the galaxies, we don't need dark matter. This is a surprise for me also, because they see they measure the acceleration, and the acceleration is inside of the in the center of the galaxies. They don't need to have dark matter. It's enough to explain this acceleration, these velocities of the stars, using the stars themselves in the center of the galaxy. Then we went, we ran to these, all the candidates that we have, and we saw all the candidates they predict a core central density profile, not a cost, but a core central density profile. That means the central density must be almost constant, and all of them predict that the acceleration goes to zero in the center of the galaxy. Fortunately, all of them can predict or can explain why they observe this acceleration. But of course, the cold dark matter model has a problem. No, they don't can explain this observation using only the cold dark matter. They have to use another physics. But the most interesting observation, and in the last time, this is in 2008, and this observation was confirmed, is that inside of 300 parsecs, all of the galaxies seems to have the same amount of mass. And here you see 6 orders of magnitude in galaxies, and all of them in 300 parsecs have the same amount of mass. That is almost 10 to the same solar masses. And this is when Jeremiah Stryker was here in Mexico and showed the first slides he showed was this one, and said there is no model to explain that. And of course, the people working in lambda cold dark matter say that they can explain that using initial conditions in the galaxies and initial conditions in the formation of the galaxies, but we must be careful. Maybe this is something artificial, and maybe it's not so bad. Okay, but let's say they can solve this problem. Very difficult, very tricky, but they can solve that. Okay, but this is the last observation. This is in 2019. This is another satellite. This is a Gaia observing the small satellites around our galaxy. And what they observe is that the satellites, the satellite galaxies around our galaxy, they are aligned to one here, so like this here. And you observe Andromeda, and they are also aligned. Of course, the lambda cold dark matter guys say, okay, we can put the initial conditions in such a way that in such a moment, all of them are aligned in this form, like in the Milky Way. But two galaxies with this alignment is so a little difficult to understand. But the problem is that the astronomers observe the third galaxy most close by to us. This is this Centaurus galaxy, and all the globular clusters around this galaxy are again aligned to this line, to the north-south line. And this is now very difficult to explain using cold dark matter, because this alignment, I think this is a challenge for all the dark matter models that exist. This alignment in galaxies, and if we can see this alignment in all of the galaxies, we have now only 3 galaxies. But if when we can see more galaxies with this alignment, then it will be very difficult that any model will explain this point. Well, now let me explain, or let me go about the alternatives. There are 2 ways for the alternatives, because we have only 2 models or 2 theories about the universe. One is the standard model of particles, and the other one is the general relativity. There is nothing else. Then we can change standard model extensions, or we can use general relativity extensions. And we cannot eliminate the standard model of the general relativity because they are very good models and very good theories. Well, in this column you have the self-interacting dark matter, warm dark matter, super heavy dark matter, self-analyzing dark matter, decaying dark matter, primordial black hole, etc. Yes, and I will explain all of them, but very shortly, very fast. And I will focus a little more in this one because it's in the last time this is a fashion. Everybody speaks about this, the Fonsi dark matter or the scalar field dark matter model. And in the general relativity extensions, we can put again the scalar field dark matter. Then we have the Mont structure, the FDR theories, maybe extra dimensions, and so on. Well, the extra dimension I will avoid, but the rest I will explain very short. Well, this is self-interacting world and world dark matter. They have a very similar structure. That means self-interacting dark matter. This is the particles in dark matter have a self-interaction, and when they are close to one to another, they have this self-interaction. Therefore, they can go far away from each other, and therefore we can explain first the center of the galaxies, the cusp. And second, we can explain why we don't have so many galaxies. And the other one, the worm, is that because the dark matter is not cold, but this is a little warm, and therefore the interaction of the temperature in these particles make that the center is not so cuspy, and the number of galaxies can be fitted. And there is a number for both of these theories. This is rho over the, this is the cross section, the density over the cross section. And the problem is that when you fit this number, Q, to have the observed number of structures of the satellite galaxies, then the cost it cannot be solved. And on the other side, when you fit this number to have the correct structure in the center of the galaxy, then the number of satellite galaxies is not fitted. That is the problem, and we have maybe a combination of them and so on can be the solution. The other one, the next alternative is primordial black holes. Primordial black holes have become a very big candidate because there is the possibility that in the beginning of the universe, the formation a lot of primordial black holes or black holes that they survived to so far. But the problem is that when they are too big, they have many restrictions. When they are smaller, in this range, then you have another restrictions, microlensing and observations. And then there is a small window here from them, and here they must be in this region. Well, then, for example, in this paper, they found that using this region for the primordial black holes, they can explain the amount of dark matter in the universe. The problem is that we have to explain why, in the beginning of the universe, we only form this black hole in this size, and not the other one, for example, in this region or this region. And if they are too small, then you have to be careful because too small black holes, because of Hawking radiation, they will radiate in gamma rays, and we don't see these gamma rays. And then they have also a very strong restriction in the size of the size of the black holes. The other candidate is now in fashion is the scalar field dark matter, and this is very simple. That I was one of the first to propose that in 2098. This is the dark matter is a scalar field with a mass. That means the scalar field fulfills the Klein-Gordon equation. And today, this model is called Bose-Einstein condensate, Fonsi wave, ultralight action, scalar field dark matter, and many names. And we did a first review, and this model become a fashion because Lamhui Jeremiah Steiker, Scott Remain, and Edward Whiting published exactly the same model that we published in 1998. And they published that in 2016. And cited this model is an absolute fashion. You can see almost every paper speaking about dark matter touch the scalar filter matter or ultralight dark matter and so on. This is really very no. We have here a review of this model, and and I will explain why this model is a fashion now. The first point is that the center density profile must be a core, because not cos. And because we have to solve the Einstein equation and the Klein-Gordon equation, in the limit and the non-relativistic limit is the Schrödinger equation, and the Schrödinger equation fulfills this the uncertainty principle. And therefore, if you have too small delta x, the moment is bigger. We have to fulfill this equation. And then if you go to the center of the galaxy, the particles will move faster, and therefore they cannot go to the center of the galaxy. And therefore they have the cause central density profiles. Here is numerical simulations, and here you have the result of these numerical simulations, and you see in the center of the galaxy with these numerical simulations, we see that the center is very core, yes, and after this point, the profile is exactly the same profile of cold dark matter. This is amazing, but this is cold dark matter, and then in the center is exactly core as we observe. Then we don't need, this model doesn't need extra physics to explain the core central density profile. And for example, here, the amount of satellite galaxies is because it is the mass power spectrum of this model, and you see at the end you have a cutoff, a very natural cutoff of the mass power spectrum, and therefore naturally this model predicts that there is no smaller halos than 10 to the 7, 10 to the 6 solar masses anywhere in the universe. Therefore, we don't see galaxies smaller than 10 to the 6, 10 to the 7 solar masses. This is the very simple and natural way to solve the cos-p problem and to solve the number of satellite time. In the last time, many people have worked in the construction of codes in order to have numerical simulations, and today these numerical simulations are the same level of accuracy of the cold dark matter. And you see here, this is the cold dark matter simulations. Here's the warm dark matter simulations, and here's the fuzzy dark matter or scalar field dark matter simulations. And the prediction is that fuzzy dark matter have interference, warm dark matter forms caustics, and cold dark matter forms subhalos. And there's a difference that we will see in the future using, for example, the results of DESI or Vera Rubin and so on. Well, but here we start with the differences between scalar field dark matter and cold dark matter. At the cosmological level, at the cosmological scales, cold dark matter and scalar field dark matter are exactly the same. There is no difference. They predict exactly the same profiles. But a small galaxy, a small scales, therefore the people is looking for this kind of models. At small scales, they have really very sharp differences. For example, here, if we compare the centers of these galaxies, what we find is that there exists this quantity or this identity where this mu dm is given by this constant. This is a constant because this is a constant, everything is constant, therefore this mu dm must be constant. And that is the density of the center of the galaxy times the center of the galaxy. Just what we observe in the universe, and this is a natural explanation of this observation, and therefore people is very excited of this model. And The other thing is that the scalar field is it's not a particle, but it's a field. And this field fulfills this Schrödinger equation together with the Poisson equation. And these equations have a scale invariance, and if we use the scale invariance in the previous formula, we see that these quantities are constant. This is the mass of the scalar field, the mu dm that we know that is a constant. That means that the center of all galaxies in the universe, the core of all galaxies in the universe will be the same. This is really very, very, very hard. But if the center is the same, and the center is almost the density constant, that means that all of these galaxies must have the same mass inside of this region. This explains exactly this formula or this observation, because you have here all of these are our satellite galaxies in 3 different RS. That is RS equal to 10. That is RS equal to 2, and that is RS equal to 0.33 kiloparsecs. That means 350 kiloparsecs. The prediction is the observation is 300. We predict 350. That means this model can explain naturally this observation that for other models are in problems, and provided that the mass of the scalar field is 10 to the minus 22 electron volts. Okay, but the most interesting thing is that this model is the Schrödinger equation, and you know the Schrödinger equation predicts the atoms. The atoms have base states, the excited states, and so on. And if we take into account the excited states, for example here, you have the base state and the excited state, and you can have the base state and the excited states in numerical simulations, both together here, and they are very, very stable. That can be also observed. And then we compare that with observations. We can see that then they can predict what we observe in the galaxies. Not that these excited states then can predict the existence of this alignment of the stars. In this case, of the globular clusters. These are the results of the scalar field. There are several. Therefore, people is now looking for these models or models related with this type. Now, then let me speak a little, very, very few about MONT in an FDR. MONT is I won't speak too much because I think Sergio has spoken about that. But what we have to change is the second law of gravity in this region of the acceleration. And that with this change, we can fit very, very well the galaxies. Maybe we have little problems with cluster of galaxies. We can claim that there exists a little dark matter, but for example, there are other solutions. The other problem of this model is that they must be covariant, and there were first attempt to this covariant alternative to the MONT. This is what was done by Bekenstein. This theory was called Tebes. This very, very complicated. I see they have a lot of terms, but in the last time they found that in this region they fit well, but in this region and in the superclusters they have problems with observations. The observations are here, and Tebes is here, and even the FDR could be here, but Tebes was away. This is another observation. Again, Tebes were here, and the observations were here, and then therefore Tebes is almost ruled out. There are people working on that, but I think it will be very difficult that Tebes can survive because it's too complicated first, and second, the observations are not well with them. Other way to solve that is we can say that the theory can be changed of scale in somehow. But this change of scale is given by these formulas, yes? And what we have to find is the way to find these formulas or to find this in a natural way. We can put that, of course, by hand, and we can solve the different scales of the theory. It's possible, but maybe we have to find a natural way to do that. But in the last time, Javier Hernandez and collaborators have found that binary stars in the universe can be explained by these Mond observations, and this is very exciting. Of course, the statistics is today very difficult to fit, but in the future we can. This is a really alternative to see that the Newton equation or the Newton law is not valid for very small accelerations. Maybe it is open. This is one thing that we have to keep in mind, and that we have to pay attention in the future. But it's very interesting. Well, then let me explain a little of the FR. FR is a new theory. Remember that R is the Einstein equation. FR equal to R. And if you change the FR, then you have the first problem. The R alone is the only theory where you have the metric tensor in the field equations in linear in second order derivatives. And this is what Einstein was looking for. But if you don't have R, but FR, then you will have 4 derivatives, and they won't be linear. They could be non-linear. And therefore you have to explain what happened when all these non-linearities and what happened with these extra derivatives in the Newton equation, because you will have that in the Newton equation. Well, you can go around of that problem, and people is working with this theory, changing a little the normative. For example, they call this Xi equal to R, and then in making this transformation, you can transform this Lagrangian to a Lagrangian of a scalar field, using a scalar field potential, very difficult, but it's a scalar field potential. And there are 2 ways to do that. For example, you can, with normal way, where the connection and the metric are related using the Christoffel symbols, or you can say no, they are independent each other, and you can make the variation using this independence and the field equations, and the variation of the field equation must give me a result of what is the connection between the connection and the metric. And this is we call this the Palatini way. And then you can go in normal way or in Palatini way, and to do the inspection of this theory. And this paper was very famous because they found that if the FR theory is very similar, or enough similar to the Einstein equations, that they can fit very well the mass power spectrum and the angular power spectrum, the CMB profile. And therefore, many people went to the FR theory, and they studied this alternative. It's open. There are many people working in this direction. Of course, they have many nice results because you can start here, and we know that if this term is very big, then you can fit everything, all the observation or relativity. But if this W is small, then you cannot fit the Einstein equations or the Einstein observations, normal observations. Therefore, this it is enough that the omega must be very big, and then you can have this one. And if you have you make a conformal transformation, you can come to the normal derivative. You have here this relation, this coupling between the scalar field and R, and here you don't have that. This is minimal coupling, this is not minimal coupling, and you can come back to the minimal coupling with this conformal transformation, and you can work here or work here, and you can see, you can say this is the physical one, this is the physical one. There are many possibilities, and therefore it is possible to have many theories about dark matter. But therefore I say theories of dark matter is very complicated, many of them. But we have to take into account the observations, the constraints that we observe, and then we can go further. Well, the conclusion is very simple. We are in a threshold for a new era of cosmology, science, and thought. Thank you very much.
Thank you very much.